start with the second speaker of this morning, Jérémie Roland, who will tell us about the quantum query complexity of sorting under partial information.
Okay, thank you. So I'd like to thank the organizers for inviting me and also for organizing this very nice conference. So this is joint work with Jean Cardinal and Gwenaël Joret. This is work in progress, but I thought that, so it's still unpublished, but I thought that it was already sufficiently interesting to present it, so I hope you will feel the same. So this is the outline of my talk. I will first introduce the problem by just talking about the standard sorting problems that you probably all know about in the classical context and in quantum context. And then I will switch to this variation of the problem, which is sorting under partial information. I will introduce the problem, introduce some techniques that were developed in the context of classical algorithms for this problem. And then I will finally get to quantum sorting under partial information. So let's start with the basic problem, sorting. So you probably all know this problem. It's a very important problem in algorithms. Probably if you had a course on algorithms, one of the very first problems that were defined was sorting. So I will formalize it here as follows. So you have a set of elements which is totally ordered under some unknown linear order. So you don't know the order of the elements. And you can only access these elements by making queries of the form, is Vi less than Vj or not? And then the query will answer, yes, it's yes or no. And so using such queries, you should determine the total order. Let's look at the classical query complexity of this problem. In classical computer science, typically we talk about decision tree complexity, because you can see any algorithm as a decision tree, because each time you perform a query answers either yes or no, so you have a decision tree. And the classical query complexity is therefore, in this case, the minimum queries necessary to solve the problem. The minimum number of queries of the type Vi less than Vj is Vi less than Vj that you need in order to completely sort your set. So classically, the complexity is well known for this problem. You probably all know it, or at least you've heard about it at some point. There's a trivial lower bound, which is the logarithm of the factorial of n, which is of order n log n. Why so? Just because it's almost a one-line proof. You have all the number of total orders. There are factorial of n possible total orders for n elements. It's n factorial of n possible permutations of n elements. And each time you perform a query, you get essentially one bit of information about this total order. And so the number of queries you need to make is the logarithm of the number of different answers you could get. So the logarithm of the number of permutations. So you get logarithm of factorial of n, which is n log n. Okay, so this is very simple. This is for the lower bound. And of course, the obvious question once we get a lower bound is it tight? And in this case, it's not so trivial, but it's not very complicated to show that it's indeed tight. There are algorithms that can solve this problem using of order n log n queries. You probably have heard about these algorithms, like the most famous examples, merge sort or heap sort. They can sort a set of n elements using of order n log n queries. Okay so far? Okay, so conclusion, the classical query complexity of sorting is n log n. And the obvious question, because of course we're interested in quantum algorithms, can quantum algorithm provide a speedup for this problem? And actually the answer is no. So I will show you in a minute why it's not possible to sort, because we can prove a lower bound for quantum sorting, which is also n log n. So in order to prove such a lower bound, we can use the standard technique in quantum query complexity, which is the adversary bound. The adversary bound says that the quantum query complexity of a problem is at least some quantity known as the adversary bound. And this adversary bound is written as a maximization problem, maximization over some matrix gamma, and then you have this expression with the matrix norms that you are trying to maximize. So just to give you a flavor, I will not go into the details of how we can prove that this is indeed a lower bound for quantum query complexity. But to give you a flavor of what it means in this case, so I wrote it for sorting, but the same technique holds for any problem in the quantum query model. So for sorting, all the matrices that are involved, so gamma, J, and delta are all matrices. And the size of the matrix in this case is factorial of n times factorial of n. Because indeed, the lines and the columns of your matrices are indexed by permutations of permutations over the set of integers from 1 to n. And so each line in each column corresponds to a permutation, and this permutation corresponds to one possible way for the query, for the oracle to behave. So for example, for permutation sigma, if you ask the query vi, is vi less than vj, the oracle will answer yes if sigma of I is less than sigma of j. So sigma really specifies how the oracle acts, or the oracle answers to your queries. In particular, it means that for permutation sigma, the total order that you're looking for, which is unknown, is v of sigma minus 1 of 1 less than v of sigma minus 1 of 2, and so on. So this is the order of the elements that you're trying to look. So each sigma specifies a given total order. And so you have all your matrices here are indexed by all these possible orders. And you also have, so gamma is a matrix you're trying to optimize, and J and delta ij are fixed. J is just the old one matrix. And delta ij is a Boolean matrix that specifies precisely how the oracle answers to your queries. In particular, delta ij is a Boolean matrix with entry y, with entry 1. Whenever, if you ask a query vi is vi less than vj, sigma and tau answer the same thing. Okay, so remember, each line, each column is indexed by possible permutations. For each entry, it corresponds to one permutation sigma, one permutation tau, and then you will have a 1 at that position if for the matrix delta ij, if both sigma and tau answer the same thing when you're comparing vi and vj. So I will not go into the details, just to give you an idea of how this thing works. So the problem now is, if you want to find a lower bound for sorting, is to find a good adversary matrix gamma. And so this was done by Hoyer, Neerbek, and Shi. And the adversary matrix they used is quite simple. So it's an adversary matrix where the element for line sigma and column tau is given by 1 over d. If tau is related to sigma by this relation, what does this mean? It means that tau is the same as applying permutation sigma, followed by a cyclic permutation of d plus 1 elements. Okay, so whenever sigma and tau have this relation, there is 1 over d in the matrix gamma. And intuitively, what that means, that tau and sigma have this relation, it means that they are essentially the same, except that one element has been shifted by d positions, because this cyclic shift here, essentially, one element at the beginning will go to the end, since you have a cyclic shift. So sigma and tau are almost the same, which means that they are very hard to distinguish. Actually, you cannot distinguish them unless you query one of the elements in this, the element that's been shifted, and one of the other elements that he had jumped over. So, so this gives you an intuition of the kind of adversary matrix you're trying to look for. You're trying to put a high weight whenever it's very hard to distinguish between two different permutations, because these are essentially the hard cases to distinguish. Okay, so without going into the details, by using this adversary matrix, they could show that the adversary bound is larger than n log n. Okay, so they get the same bound as the complexity of the classical problem for sorting, which means that we cannot hope to get any quantum speedup. So in this case, for sorting, there's no use for quantum computers. A classical computer can do just as well. Well, maybe you can gain a little bit on the constant, but the scaling will always be n log n. Okay, so this is for the simplest case of sorting a total order. And now we switch to this perhaps more interesting problem, or at least less trivial problem. Well, it's not so trivial for sorting because the lower bound is not so trivial, but this problem has been solved for sorting like 15 years ago. But sorting under partial information, it's more complicated, and even in the classical case, it's quite complicated. So what is this problem? So it's again a sorting problem. So you have a set of elements which are totally ordered by some unknown linear order. So you know that there's some order for all these elements, and you want to sort them. But the difference now is that you're not given only the set, but this set is given to you as a partially ordered set. So in short, it's called a pose set. A pose set is a partially ordered set, which means that you know the elements and you already know some of the comparisons between these elements. Okay, so a pose set specifies a partial order between elements. So some comparisons are fixed and others are not. And the idea, of course, is that the pose set that it provided to you is consistent with the total order. So, of course, whenever the partial order tells you that Vi should be less than Vj, then it means that for the total order that you're looking for, Vi is indeed less than Vj. So essentially what this means is that since this partial order P is given, you already know some of the comparisons. Okay, so for some queries, you already know the answer. Okay, so it should make the problem easier. But on the other hand, it makes it harder to find an efficient algorithm because you shouldn't waste your time querying things that you already know. Okay, so but the problem is still the same. You're trying to, given this partial order, you're trying to determine the total order by making queries of the form is Vi less than Vj. Okay, is this definition clear? It's quite simple, right? So you're just sorting, but you already know some of the comparisons. Okay, so let's try to analyze the classical query complexity of this problem. So the complexity will be characterized by the number of linear extensions of P. So what is a linear extension? It's a total order that is consistent with P. Because since you know that the total order you're looking for is consistent with P, you know that it has to be one of the possible total orders that are compatible with P. So you're looking at all the total orders that are compatible with P, and you know that one of them is the one you're looking for. So, so we will call E of P the number of total orders compatible with P. And so there is a trivial lower bound again, which is the logarithm of this number. Again, each time you perform a query, you can acquire at most 1 bit about the solution, and you have E of P possible total orders. So you need log E of P queries at least in order to be able to determine each one of them. Okay? So this is, again, like a trivial lower bound. The proof is exactly the same as for the regular sorting problem. Now the problem is, can we design an algorithm that matches this lower bound? Of course, you could just use the algorithm for sorting, but then it would take n log n, and n log n might be larger than log of E of P. Okay, so maybe there's something better that you can do. Okay, so in order to design a good algorithm, when you think a little bit about it, there is this notion of balance pair that appears naturally. So let me explain you what this is. Suppose that you have your pose set, your partially ordered set, P, with some number of compatible total orders E of P. And then at some point, well, you start by performing a query. Is Vi less than Vj? Is V less than W? Once you get the answer to that query, you can add the answer, so either V less than W or W less than V, to your partial order to get a new partial order. So you can update P. Okay, so each time you get information by performing queries, you can update P. And what happens is that each time you add relations in your partial order, the number of compatible total orders decreases, of course, because all the ones that are not consistent with the answer that you just received are not possible anymore. So if I call PW the new partial order, once you add the relation V less than W, you know that E of P less is less than E of P. Okay, you reduce the number of possible total orders that are compatible with everything you know so far, essentially. Okay, so of course, if the answer is no, if V is not less than W, so if W is less than V, you can update in the other direction, and you get another new partial order. And of course, again, the new number of options is less than the former one because you have more information, so there are less total orders that are compatible with whatever you know at that point. And of course, you also know that the sum of these two is what you had before, okay? Because among all the partial orders that are compatible with P, some of them have v less than w, and some of them have v larger than w. Okay, so this really splits into the partial orders. So if you sum the number of this number and this number, you get the total number of options. So when you think about it, when you perform an algorithm, what you're hoping for is that essentially at each time, you would like to reduce the number of options by a factor of 2. Okay, because this makes the total number of options decrease as fast as possible. So what you would like, ideally, it's not possible to achieve this, but ideally you would like both of these numbers to be approximately the initial number divided by 2. Okay, because this is how you gain information. Essentially, this means that you get exactly 1 bit of information in information theoretical terms each time you perform a query. Okay, so this you cannot get exactly, but what was proved in various theorems is that you can get something which is more or less approximately balanced, meaning that you can get that for any p which is not a chain is a total order. Everything, you know, all the relations. So of course, in that case, you cannot do anything because the problem is already solved. But whenever you have a partial order which is not a chain, so some comparisons are unknown, you can find a pair of elements for which the comparison is not known, such that if you add v less than w to your partial order, the number of possible total orders compatible with this new partial order is between delta E of p and 1 minus delta E of p. Okay? So if delta was 1/2, you would get exactly this. But you cannot get this with delta equals 1/2, but you can get this with delta being a constant, which is already good enough. So this was proof for some, so we can show that it's true for some absolute constant delta, and over time this constant delta has been improved. Of course, we would like to get as close as possible as 1/2. So it was originally proved with delta is 3/11 by Kahn and Sachs in 84. Then it was slightly improved like in 95. And actually there's a conjecture that the optimal is delta equals 1/3. This is called the 1/3, 2/3 conjecture. So you can get to 1/2, but you can get to each time you would have a separation 1/3 on one side and 2/3 on the other side, which is already quite good. So I will not go into these theorems, but from this theorem, we immediately get an algorithm for sorting on the partial information. So this is the algorithm we get. If we are given some partial order P, we first look for a delta balance pair VW, so a pair that satisfies the theorem I showed in the previous slide. I query this pair, is V less than W, and then I get an answer, and I update P according to the result. And now I know that this number E of P will decrease at least by a factor delta, I guess. So the algorithm uses less than log 1 over, so maybe it's actually 1 over 1 minus delta, what I wanted to say, but the algorithm uses essentially the log 1 over P queries. So this is tight. Okay, of course you can improve the constant by improving delta, but nevertheless it's always log E of P. So this matches the lower bound we had before. So it looks like we have an optimal algorithm and that we're really happy. There's one problem with this, is that actually if you want to use this algorithm, you need to be able to track E of P in order to check that the pair you have is indeed delta balanced. And computing E of P for a given partial order is actually a sharp P complete problem. So it's a very hard problem. And this means that even though we will not use a lot of queries, we will spend a lot of time computing E of P. And this is very bad. So the idea is to find a way to approximate E of P. And this way, instead of computing E of P exactly, which is sharp P complete, we will find an approximation of E of P faster, and then use an algorithm which is similar to that one, but which will not have this disadvantage. Okay, so in order to understand how we can do that, how we can approximate E of P, we need to go a little bit into the theory of sorting. And I need to introduce first the notions of polytopes that are related to sorting problems. So in all that follows, I always fix a poset P, so partial order P over a set of n elements. And the first polytope I will define is what is called the order polytope. So the order polytope is a subset of the hypercube, if you want. So it's a subset of points in the v-dimensional space, where all the coordinates are between 0 and 1. So it's really a subset of the hypercube. And no, of course, it has to be related to the partial order P. And it's related in that sense, is that whenever V is less than W for this partial order, the coordinate xv should be less than the coordinate xw. So if you want, the coordinates of your point should satisfy the same relations as what is imposed by your partial order. So if it's not clear, let me give you an example. So I will always use this graphical representation of a partial order. So here, when I have, so I will have a graph where I have a vertex for each element. And when I have an edge between two elements, it means that these two elements are, there is a comparison that is imposed between these two elements. And in particular, this imposes that the B element is larger than the A element. Okay, so whenever you have an edge between two elements, the one on the top should be larger than the one below. So here, it's a pose set over two elements with only one comparison which is imposed, which is B larger than A. And so the order polytope in that case, so here it's just a square because it's only two-dimensional. So it's a subset of the square. And so XA and XB should be between 0 and 1. And also, since I have this constraint between A and B, XA should be less than XB. Okay, and so I get this triangle here. Okay? So let me show you a slightly more complicated example, not much more complicated. Here I only have 3 elements, so it's a 3-dimensional example. Of course, with 4 elements, I should require a 4th dimension. It will be harder to show, so that's why I stop with 3. So here, this partial order is a partial order over 3 elements, where B is larger than A, C is larger than A, but B and C are not comparable. Okay, so it's a slightly less trivial example of a partial order. So again, XA and XB, and for this order polytope, XA and XB and C should be between 0 and 1. So again, it's a subset of the cube. And I have 2 relations that XA should be less than XB, and XA should be less than XC. Okay? And you get this pyramid here when you impose all of these things. So you always get a polytope. That's maybe the thing to remember. So if you think, I mean, you can check that indeed the set of points that satisfy these relations here exactly correspond to this pyramid. Okay? So why is this polytope interesting? Because we can relate the volume of the polytope to the number of linear extensions, so the number of total orders that are compatible with the partial order P. So recall here, n is the number of elements in my set, and E of P is the number of linear extensions of P. So remember, linear extensions is just a total order compatible with P. And we can show that the volume of the order polytope is equal to this number of linear extensions divided by factorial of n. And actually, it's not so complicated to show that. The idea is that every linear extension of P, so every total order, if you want, defines a simplex of the order polytope. And every simplex has the same volume. So essentially, if you consider the full hypercube, the hypercube will be divided in all possible permutations, depending on the order of the coordinates. The hypercube will be split into all possible permutations, and there are factorial of n possible permutations. So we have factorial of n different simplices, and the volume of the hypercube is 1, so the volume of each simplex should be 1 over factorial of n. So each simplex has a volume 1 over factorial of n, and the order polytope consists of exactly E of P of these simplices. Okay, so you get that the volume of the order polytope is E of P divided by factorial of n. Okay, so this is a nice graphical representation of this relation. Just to give you an example again, let's look at this partial order where A is less than B and A is less than C, and B and C are not comparable. So if I look at the order polytope, it's this pyramid that I showed you before. So this pyramid, you can split it in two, because there are two options for B and C. Either B is larger than C, either B is less than C. So in this pyramid, there are some points such that XB is larger than XC, and some points such that XB is less than XC. Okay, so this splits the pyramid in two, so according to this line here. So I get these two, I get one simplex for each option. So the first option is when C is larger than B, so I get this volume here. And the other option is when B is larger than C, I get this other option here. And if I take the union of these two things, I get my order polytope. And each of these simplices, I can show that it has volume 1 over factorial of n. So here, the volume is 2 over factorial of n, because indeed I have two total orders that are compatible with my partial order. Okay, because there are two ways to order B and C. Okay? Okay, so let's continue. So this is the first polytope. There's a second polytope I need to introduce, which is a chain polytope. So the chain polytope, first I need to define the notion of chain. A chain in a partial order is a set of elements for which I know all the comparisons. Okay, so within a partially ordered set, I can take a subset. Sometimes you can take subsets that are completely ordered. Okay, so and if they are completely ordered, it means that for the subset, I can show that V1 is less than V2, less than, and so on. So this is what is called a chain. I will give another example in a second if it's not clear. So you can take subsets of elements which make up a chain. And then the chain polytope, it's again a subset of the hypercube, but the constraint now is that whenever I have a subset of points which make a chain, the sum of their coordinates should be less than 1. Okay, so for every chain C in P, the sum over V in C of XV should be less than 1. Okay, so this is the definition, but it's maybe clearer with an example. So let's take the same example as before. I have this partial order where B and C are incomparable, and B is larger than A, C larger than A. So here I have two chains. I have a chain consisting of A and B, and another chain consisting of A and C. Okay, so this means for the chain polytope, XA plus XB should be less than 1, and XA plus XC should be less than 1. And if I impose all these linear constraints, I get another pyramid, which is not the same as for the order polytope, but it's again a polytope. Okay, and this is a chain polytope. Okay? And now the nice thing is that there is a very close connection between the order polytope and the chain polytope. Actually, we can map the order polytope to the chain polytope by using this map. So if X is a point of the order polytope, I can find a point of the order polytope Y by using this construction. So if V is a minimal element, so an element for which there's no element which is known to be smaller, then YV is the same as XV. But if there are some elements which are smaller than XV, then I take the one which is the largest one, and I take XV minus XW. Okay, and this is my YV. And if I do that, we can show that whenever X is a point in the order polytope, Y will be a point in the chain polytope. And this map phi has also nice properties. It is continuous, piecewise, linear bijection from O to P2. So you can go back from one polytope to the other. And so let me just give you an example. I take again, so here I take a total order, C larger than B larger than A. So here is my order polytope, here is my chain polytope. And for example, I will take the point, this point in red here as coordinates 1 half, 1 half, 1. So it's indeed a point of the order polytope because indeed 1 is larger than 1 half, which is larger or equal to 1 half. Okay, so this is the point of the order polytope. And when I use this map, I get 1 half, 0, 1 half. So here A is a minimal point, so 1 half remains 1 half. B is not a minimal point, so from 1 half, I remove the coordinate of the point just below, so it's 1 half minus 1 half, so I get 0. And again for C, 1 is not a minimal point, so I remove the coordinate of the point just below, so I have 1 minus 1 half, which is 1 half. So I get as new coordinate 1 half, 0, 1 half. And this is indeed a point of the chain polytope, because for any chain, here I only have one chain, A, B, C, the sum of the coordinates is less than 1. And you can check that, you can prove that this works for any chain. Okay, so there's a nice connection between the two. And what is really nice is from this connection, we can prove that the volume of the chain polytope is the same as the volume of the order polytope. Okay, and remember we were interested in that volume because this volume is related to the number of total orders, and this number of total orders is related to the complexity of the sorting algorithm for this partial order. So that's why we were interested in those polytopes. So this means now that we can work either with the chain polytope with the order polytope if you are trying to estimate E of P. Okay, so far? Okay. So now, in order to estimate E of P, we cannot directly compute this volume because it's quite complicated, but what we can do is try to estimate the volume of these polytopes. And the way we estimate the volume is by approximating them by the volume of a box, which is included into the polytope. So this kind of picture you should have in mind. I have a polytope here, this prism with a triangular basis, and I have inside a box which lies inside, and obviously the size of the box is less than the size of the polytope. But the idea is that if I take the largest box, it shouldn't be much less. That's more or less the intuition you should have. So the idea is that for each, so we'll use a chain polytope, and for each coordinates, for each point in the chain polytope, we consider the box between the origin and x, such that the origin and this point x are opposite corners of the box. So remember, the chain polytope looks like this. So you can take the box where 0 and any point in this chain polytope are opposite corners of the box, and you can form a box with this. And since the chain polytope always includes, first it's a polytope, it's convex, and also it always includes the origin. For any point you consider in the chain polytope, when you make that construction, you will get a box which lies completely inside the polytope. And that's the idea. Okay, so now we're trying to optimize, take the largest possible box. So the volume of a box, since it's just a box, the volume is just the product of all the coordinates. Okay, it's a box starting at the origin and going up to x. So you just multiply all the coordinates, you get the volume of the box. So you try to maximize the volume of the box for all the points in the chain polytope. Now, since it's not really the volume that we are interested in, but the logarithm of the volume, because remember, the complexity of sorting algorithm is related to the logarithm of the number of linear extensions. So we take the log, and just to make things nicer, we will normalize and change the sign so that we get a positive number. And so we take the log of this thing, and we multiply by minus 1 over n, and now we get this thing. So it's exactly the same as this. It's just minus 1 over n log of this. So we get this, and this we define it as being the entropy of the partial order. Why do we call it an entropy? Because it has properties similar to entropy, but also there's a nice connection with graph entropy. So there's a notion of graph entropy introduced by Kerner in '73, and the entropy we get here is actually the graph entropy of the comparability graph of P. So this graph where you put an edge whenever two elements are comparable or not. Okay, so this is closely related to notion of graph entropy, and here we call it the entropy of the poset, the entropy of the partial order. Okay, so we will try to use this entropy to estimate the volume of the box, so the volume of the chain polytope, and therefore the number of this number E of P. Okay, so remember the volume of the chain polytope is E of P divided by factorial of n. So now in this entropy, we have taken the log and multiplied by minus 1 over n. So if we do that for this volume, we get n log n minus the log of E of P plus some linear term. So the idea is that we will use this entropy as an approximation of this number, n log n minus log E of P. So the idea is that when we take this box and we take minus 1 over n, the log of this box, we get something which is close to minus 1 over n log of the volume of the full chain polytope. So since we have n log n, since this entropy approximates n log n minus log E of P, and what we are interested in is actually log E of P, we can introduce a dual entropy which is log n minus the entropy. And this way, nh of the dual entropy will be log of E of p. Okay? Log of E of p is what we're trying to estimate. And actually, we can prove that this is a good approximation. And this entropy, oh, there's an n missing here. N times the entropy is equal to log E of p up to some constant. Okay, so this is a good approximation. So again, the constant has been optimized over the time. So originally it was about 11, and more recently it was proved that we can take c equals 2, and this is actually tight. In some cases, there is indeed a factor of 2 between the two. This was actually proved by my co-authors and some of their collaborators. So, this entropy gives really a good estimation up to a factor of 2 of the log of E of p, which were what we were trying to optimize. So now we have, okay, I think I will skip that slide because otherwise I will not have enough time. So now we can use this entropy to, so maybe just tell you what we get in here. We get, these are properties of the entropy, and one thing we can show, for example, is that this entropy is a number between 0 and log n. So this already gives you an idea what we call this an entropy. That's all of the interesting properties. But okay, so we will use this notion of entropy to make a better algorithm for sorting under partial information. And the idea is that we will have an analog of this notion of balanced pair, but not for the number of linear extensions, but for the entropy. So this is this analog. Kahn and Kim have shown that for any chain, for any partial order which is not a chain, so whenever there are some pairs that are not comparable, there exists an uncomparable pair such that the maximum of the entropy that you get after adding either V less than W or V more than W is less than the entropy minus C. So the entropy, n times the entropy decreases by a constant each time you make a query, essentially. That's what it means. And of course, this is very useful for an algorithm, because it decreases by a constant, so you know that we will have to repeat this of order nh of p times. Okay, so we'll get to this in a second. So this theorem is really similar to delta unbalanced pair, but using the entropy instead of the number of linear extensions. And we know that one is a good approximation of the other. So, and the good thing, this is why it's useful, is that this entropy can be computed efficiently, which was not the case for E of p. Okay, so now we are in a good shape to make a good algorithm. We use essentially the same idea as before. So whenever we have a P, we find an incomparable pair VW as in the previous theorem just before. We query V is less than W. We update P according to the result, and we repeat until P is a partial order, so until we have completely sorted all elements. And now, how many queries the algorithm will use? But we start with an entropy which is n of p, and each time it decreases by a constant, so you need to repeat it of order nh of p times. And we know that nh of p is up to a factor of 2, the same as log E of p, and so you get the same complexity as before. And also now, this algorithm is polynomial and indeterministic. The algorithm before was not was also deterministic, but it was not. It was really time expensive. So here we have all the properties that we wanted. Okay, so this is it for the. I took most of the time of my talk for the classical part because we needed all these notions. And now let's go to the quantum part. So only have, I think, less than 10 minutes maybe. We started a few minutes late. Okay, let's see. Let's see if quantum algorithm can help in that, can provide a speed up for sorting under partial order. So can we make better than log E of p, essentially? That's the question. And again, of course, if we want to prove a lower bound for this problem, we can use the adversary bound. And in that case, the adversary bound has a very similar form. The only difference is that the matrix, all the matrices that are involved, instead of being factorial of n times factorial of n, there are only E of p times E of p, because you only have to consider the permutations that are consistent with your partial order. So you have less possible options. So all these matrices are smaller. But apart from this, it's exactly the same form. So now lines and columns of the matrices are indexed by permutation sigma that are consistent with your partial order. And so Yao attacked this problem, and he thought that actually the adversary matrix used by Hoyer, Neerbek, and Shi for the standard sorting problem might work. So he used the same adversary matrix, he just took the same matrix and he removed all the lines and columns that were not consistent with the partial order. So he gets a submatrix of this matrix P. And using this matrix, he was able to show that the quantum query complexity of sorting, so the adversary bound, was given by this expression. So in this expression, you have an expectation over all permutations consistent with P of this sum here, which involves the harmonic numbers. Okay, so let's not go into the details of this lower bound, but this is the expression he gets. And also, it involves this dV of sigma here, and this dV of sigma is defined by this thing, which is very similar to the map from the order polytope to the chain polytope. It's not an accident. The only difference is that instead of having the coordinates of a point in the polytope, we just have the integers, the permutations of the integers here. So all these things are integers now. But apart from this, it's essentially the same map that we use. And actually, that's what he will use to prove a bound. So he conjectured that, so from now on I will call QLB this expression proved by Yao, and he conjectured that this is tight in the sense that this provides the same bound as for the classical algorithm, that we cannot get a quantum speedup. So he conjectured that QLB is at least C log E of P. And using connection with graph entropy, in particular this chain polytope and this order polytope, he could show almost this except that there is a linear loss here, okay? And this linear loss actually is quite bad because log E of P is at most n log n, okay? So you have n log n, at most n log n minus n. So for all the partial orders that are not between n and n log n, you get a trivial bound, okay? So you get a trivial bound whenever log E of P is less than O of n. So for partial orders where you don't have a lot of comparisons, where the E of P is close to n log n, it's fine. But whenever you have many comparisons, this will not give you a tight bound, for sure. You will get a trivial bound of 0, or something negative, actually. Okay, so that's not good. Well, that's good, but that's not good enough. Okay, so I don't have so much time left, so let me just explain the idea behind his approach and how we can improve on it. So first, for some reasons, let's use natural logarithms instead of log 2. But we can define the same entropy as before. And since it's just a change of basis of logarithm, we also have that nh of p is larger than ln of e of p. And what Yao could prove is that this bound QLB that he proved is at least n times the expectation over the chain polytope of this quantity. And now remember that the entropy was the maximum over the chain polytope of the same quantity. So essentially, he gets exactly what he wants, but he has an expectation instead of a maximum. It would be okay if the expectation is close to the maximum. In that case, we will get the same bound. But the only thing he could prove is that the expectation is at least the entropy minus a constant, a large constant. And in the bound, everything is multiplied by n, so you get this linear loss that he had. So unfortunately, it's not good enough. So remember just the picture. This entropy was related to the size of the maximum box in this polytope. And now the bound that Yao obtained is some average version of this. So you average the log of the size of the box for all points in the polytope. And the question is this average close to the maximum value? Okay, so that's what Yao proved more than 10 years ago, I think. And finally, in the last few minutes, I will say you a few words about our contribution. So the first thing that we showed is that the bound based on the expectation cannot be tight. Why it cannot be tight? Because in some cases where it gives you a negative number. So very simple, this is a trivial example of a total order. So if you're trying to solve a total order, there's nothing to do. Okay, so the bound is 0, that's fine. But nevertheless, this expectation gives you minus gamma n, where gamma is this Euler-Mascheroni constant. So this gives you a negative constant, or it's still fine because it's a trivial problem, but still it gives you something which is minus a linear function in n, which is which doesn't look good. And in particular, if in addition to this chain I had just one element, which is incomparable here, the problem now is to find where these elements can be inserted. Okay, so this is called ordered insertion, which you can solve by dichotomic search. Okay, you can find where this element should go by performing dichotomic search in this chain. So the complexity should be log n, and this bound gives essentially log n minus again this gamma n. So this is negative, and so this doesn't give you a bound for this problem, which is non-trivial. And actually, we considered other examples, and each time we got the same loss of minus gamma n. We thought, okay, this cannot be a coincidence. There has to be something deeper there. And remember that gamma is actually the large n difference between the harmonic number and ln of n. So actually, and when we realize this, we say, okay, maybe there's a thing, there's an ln of n here. What happens if we replace ln of n by harmonic number in this case? And actually, by making a final analysis of Yao's lower bound, we could prove that his bound is actually equal, it's exactly the same thing, as what he proved before, but by replacing the logarithm by the harmonic number. Okay? And this, when we get this quantity, we don't have this loss here. And it seems like it might work. So just the proof is based on again, the same techniques using these polytopes and this map from the chain polytope from the order polytope to the chain polytope, and some technical lemma related to harmonic numbers and expectations of logarithm of coordinates over these polytopes. And now actually we conjecture that this new bound is tight, meaning that the expectation over the chain polytope of this quantity is up to a constant the same as the maximum of this quantity. And this gives you the entropy, and if this is true, it means that the quantum lower bound is the same as the classical complexity. Okay, so we were not able to prove this conjecture for any poset. This is why this is still a work in progress. But we could still prove it for an extended class of posets. So we could prove it for a so-called series parallel posets. So we can show that for any series parallel poset, we indeed have this bound with C, which is 0.72. So essentially, the expectation is the same as the max up to this factor. Okay, so that in all these posets, this is a good approximation. So what is a series parallel poset? These are posets that you can obtain by starting from single elements and combining them using two compositions, parallel compositions and series composition. So parallel compositions is very simple. You take two different posets, or two different sets of elements with some partial order between them, and then you take them together. Note that this is not a trivial composition, because now when you're trying to sort this thing, not only you have to sort these elements between each other, these elements between each other, but also you need to find the relations in between these two posets. Okay, so this is called a parallel composition. I take two posets, I put them together, and I get a new poset over a larger set of elements. This is the parallel composition. The series composition is similar, except that now you take your two posets and you put them on top of each other. And you add all the possible connections between the two. So all the elements of the upper posets should be larger than all the elements in the lower poset. And now, by combining these two things, series composition and parallel composition, as many times as you want, you get what is called a series parallel poset. And many posets actually have that form. Many interesting posets have that form. And in that case, we were able to prove that the conjecture is correct. So we show that in that case, essentially the average entropy and this max entropy behave the same. So that's how we prove this thing. We show that the average entropy and the max entropy behave the same under series composition and under parallel composition. And the main theorem is then proved by induction over the size of the poset. So we start with small poset, we show that it's true, and by induction we show that each time we compose, this relation remains correct. Okay, so it's almost in time, I think. So thank you. So indeed, of course, this is work in progress. We hope now to extend this to all possible posets and show that indeed, unfortunately for us, quantum computers cannot help for this problem of sorting under partial information. Thank you.